Hey, Tisham, how are you?
Assalamualaikum, sir. Alhamdulillah, I'm good, sir.
Aslam. You usually come on time, I mean, before time usually.
Yes, sir.
Why are you so punctual?
Sir, I try to be punctual. I want to be in your good list. I think that's right.
Good. That's good. So, David, how are you? How is going? I'm okay. So, you are busy in these days? Because before you were not sure that you will. Uh, yeah, okay, okay. Mhm, mhm. And what do you teach there? Ah, okay. And physics also? No? Ah, okay, okay. So, the students are good? Mhm. Okay, okay. Good. So, Marcio, are you? Roshio?
Hello.
Yes,
Hi.
hello. So, how is going?
Well, I'm doing well. It's normally not normal.
So you are, I mean, doing your project at the university?
Yes, I already finished the some advances, and I send it to my
Advisor.
yes.
And
But
what you
well,
are, but still you
yes,
go to university.
yes. Maybe next year, um, I can finish the bachelor BBS.
Mhm. BS in physics or what? Electrical or what?
Yes, BS in physics.
Mhm. Okay, good. Okay, so Nargis Ghafoor,
So,
how
Assalamualaikum,
are you?
sir.
Walaikum salam.
I'm doing
How,
good.
how is going?
Alhamdulillah. All is fine.
Okay, good.
Yes,
Did
sir.
you go through the previous lectures?
Yes, sir. Yes, sir. I've completed all that.
Mhm.
I was late. I was late to join, and I've
Mhm.
completed.
Okay,
And now I'm
it's good.
with the pace, matching the pace.
Okay, it's good. And Zanfar,
Song, sir.
Islam. So how is going?
Alhamdulillah, sir. Everything's fine.
Everything's fine with you?
Yes, sir.
Punctual now?
Inshallah,
Or
sir.
try to be? Or try to be?
Sir, I will try my best.
Okay. Okay, so what we're studying in the last lecture, probably I don't know. I mean, if you people went through the previous lectures, so we were studying about the mode locking, isn't it? And mode locking, number of, I mean, different kinds of mode locking, definitely. Just a minute. Okay, so probably you people can see now.
Yes,
You
sir.
people
We
can
can
see.
see.
Yeah. So the thing is that
Sir,
yes.
sir, please start the recording.
Oh, Okay, so what we were studying in the last lecture, that was related to, not related to actually, it was actually mode locking. And mode locking, different kind of mode lockings, okay. We went through the mode locking, which is called active mode locking, okay. So active mode locking, when you use something in the cavity, some devices, optical switches, okay. And there were some disadvantages of mode locking, active mode locking. And if you have gone through the previous lectures, probably, perhaps, then you could understand the things. And today, actually, I wanted to ask some questions to you people, but I don't see many people. 3 people, they are absent. They already mentioned to me. And rest, I think, so probably 3 or 4 people are missing. So I wanted to, kind of brief overview that you people are really understanding or not. And but anyway, because there are less people here today, so maybe in the next lecture. Okay, so now other kind of mode locking, which we call the passive mode locking. Okay, so passive mode locking, basically, in that kind of mode locking, we don't use any kind of, we use something in the cavity, but it's not like any optical switch or something like this. Okay. So, like, we are not using the acousto-optic device, or we are not using any kind of electro-optic device, and but we are using something which is called saturable absorber. Okay. So I don't know how many people remember that what was the saturable absorber. So probably Gazanfar, do you know what is saturable absorber?
Yes, sir, sure.
Tell me.
Sir, when we actually when some kind of energy is stored by a system, then it will uh, get out that energy in one pulse.
Yeah, somehow, but not exactly. I mean, it's supposed to be.
Yes,
Um,
mainly the dyes we use as a saturable absorber.
yeah, it absorbs and then bleach.
Yes.
So this is something like this. So if we move to the next slide now. Okay, so next slide. Just a minute, let me activate my pen. Okay, so this kind of mode locking, basically, saturable absorber-based mode locking, and it's passive mode locking. This is not, I mean, there are 2 categories in categorized into 2 kind of passive mode locking. The first one, which I started here, is the saturable absorber. So if no mode locking, then you don't have pulse laser. So mode locking is very important, the ultrafast laser, femtosecond laser, all kind of ultrafast laser actually. Femtosecond is one of the ultrafast laser. Ultra short, ultra fast. So if you see here in this diagram, which is very simple diagram here, so you have gain medium and you have saturable absorber, and this is a cavity mirrors. Okay. So the light pulse moves back and forth. Okay. And it passes through the gain medium and also passes through the saturable absorber. In the gain medium, it amplifies. And here, in the beginning, when the intensity is low, then we have high loss. High loss means we don't get any output. Okay. And if we don't get any output, it means it's losses. But when this intensity is increased, because pumping is going on, if you remember the previous lectures, pumping is going on and population inversion is going on, and it's building up. The gain medium is there, and so the intensity at the beginning was low, so stopped by the saturable absorber. Then the intensity is increased slowly. When the intensity is increased, then the saturable absorber become transparent. It's bleached. So it cannot absorb any more current. So it means the light will pass through and we get a pulse. In simple words. And these saturable absorbers are usually dye materials, dye liquids actually, not materials. So, and also there are some other kind of existing, I mean, if you remember in the last semiconductor type, dye mediums, and not dye mediums, so saturable absorbers. So what it does at low intensity in the beginning, it blocks. And when the intensity is increased, the light passes through the saturable absorber and it releases the light. So it's bleaching effect. Okay. And so the important thing here, amplifier, medium, gain medium, and the saturable absorber. They should how, not should how, actually somehow they, I must say that compatible to each other. How we'll see later in the coming slides. So now these are steps actually. And these steps will help you to understand. So like, as I mentioned that saturable absorbers, they are dark. Dark means they absorb everything. We don't see anything outside of that saturable absorber. And it becomes transparent at high intensities. The bleaching effect is bleaches. Okay. And the second, actually, the point here, what we have in the beginning. In the beginning, when we start the laser, as I mentioned before, we have some light, which is not exactly coherent, somehow partially coherent, is noisy, is spontaneous, some random spikes, but it's very usually, I mean, like in a fraction of seconds or something like this in the beginning. And with the passage of time, so definitely these kind of noisy and spontaneous light, actually, it is stopped by the saturable absorber. And when we have a proper laser action, then like brighter one, real one, so then it bleach and it pass through the absorber. And the losses reduce. So when the light passes through the saturable absorber, then the losses are reduced. Okay. Now, if we move further here, what it says, spikes. So what we get at the output after bleaching, the pulses, okay? And these pulses are, so these pulses are the pulses which are mode lock pulses, and that's what we need, okay? And then this pulse amplify, make a round trip in the cavity, and we get at the partially polished side of the cavity. One of the important thing is that recovery time. So this kind of saturable absorbers, they recover within a fraction of seconds, and they are ready for the second pulse. Okay, so it happens quickly, very quickly, and it becomes opaque again, dark again, and then after a while, bleaching effect will start. So this is called a fast recovery or recovery time, okay? And the thing which is when it is started, it's kind of, I mean, like you can say it's a filtering effect, like some kind of random fluctuations or peaks or something like this. These are attenuated, low intensity fluctuations or noise or something. These are attenuated and absorbed in the saturable absorber. So it's filtering as well. So it will give you, we will get at the output very nice and clean pulses. Okay, so it can also help to clean the pulses as well. And so the strongest one, the spikes or the pulses, it passes through the absorber, amplify, and we get at the output of the cavity. Others absorbed or faded out, something like this. And next, here, periodic exit. So periodic exit means that after a round trip time, every round trip time, one round trip, okay, and it hits to the output coupler or the mirror, and we can take it as an output. So this process is repeated, and you get the pulses in a very short interval of time, actually. And it can be, we call it repetition rate, like after how many seconds or fraction of seconds, one pulse comes. We are not saying the pulse for how long it stays, but after how many seconds, minutes, pulse comes, is called the repetition rate. So like here, if this is your pulse and second pulse is here, so the time between them, we call it repetition rate. It's 1/t, okay? And this thing actually, this we call duration of the pulse, for how long the pulse stays. So if we say ultra short pulses, then it means it must be picosecond or femtosecond. Attosecond is a different story. Okay, and this repetition rate, it depends on the cavity. Okay, length of the cavity and etc., different things. Okay, so decay or recovery time, as I mentioned, that it recover quickly the saturable absorbers to ready for the second pulse, something like this. And I also mentioned that the gain medium has to be compatible somehow with the saturable absorber. And that thing is explained here somehow. We know that the gain medium it has a decay time. Okay, when it emits the laser from metastable to the lower level or to ground level. So it's a decay time. Okay, and in case of Nd:YAG, this time is around 230 microseconds. In case of TISF, this is around 3.2 microseconds. Okay, so Nd:YAG is a bit longer, decay time. TISF is shorter, very short. So that is why Nd:YAG cannot be used actually to produce a femtosecond laser. This is one of the reasons actually. And a femtosecond can be. Now, saturable absorber, it's a recovery time. Gain medium decay time and, excuse me, gain medium decay time and saturable absorbers recovery time. So in case of Nd:YAG, it's a 230 microseconds. And in case of TISF is 3.2 microsecond around about. Now the saturable absorber, it is recovery time actually in case of if we use an organic dye like rhodamine 6G or something like this, which is used to dye your hairs as well and also to dye the clothes or something like this. The recovery time in case of the organic dye here is nanosecond to microseconds. Okay. So, I mean, it should be, as I mentioned, that it should not be very long recovery time. In that case, it may not be possible to get the more log pulses. You will see in the coming slides actually what will be the situation. Organic dyes and now, as I mentioned, that semiconductor type saturable absorber also exists, SISAMs. And SISAMs actually is called semiconductor saturable absorber mirrors. Okay. And in the previous slide, I think I've shown you the diagram also, this kind of absorbers. So these are manufactured kind of absorbers which are available in the market. And their recovery time is picosecond to nanosecond. In case of organ dye, it's a nanosecond to microsecond. Okay. So definitely semiconductor type is much more efficient, recovery time is shorter. So it's more promising to use this kind of absorber to have a shorter pulse. And saturable absorber is not only used to have a mode lock, very short pulse, it also used, if you remember, in Q switching process. Okay. So for a Q switching, you don't need very small recovery time or very short recovery time in case of saturable absorbers. But in case of mode lock lasers, you need shorter recovery time. Okay. And also these saturable absorbers, they are also used for to clean the pulses as well, as I mentioned to you, to remove the unwanted noise and spikes and something like this. Okay. So now if you move to the next slide, it will give you the idea. So comparison is given that what will be the laser behavior if you have a if you compare the recovery time and the gain, decay time of the gain medium. So you see here, this one, saturable absorbers, recovery time is less than decay time less than decay time. Okay. And what happened in this case, that absorber recovers much faster than the gain. Okay, much faster than the gain. And then we get the mode locking, mode lock pulses. It can be a femtosecond or it can be a picosecond. If here almost equal the decay time and the recovery time, then you may get a Q switched pulse. Not very short pulse, but Q switched pulse. And it may give you some unstable kind of pulses. May not be 100% Q switch pulses or something like this. So in this case, absorber and the gain recover on a similar time scale, which is not needed. Here, if you have a decay time less than the recovery time, so obviously, if the decay time is less than the recovery time, then it's by sure it's Q switch, and absorber is slow, okay, because recovery time is greater than the decay time, and it must be a Q switch type arrangement, and we get the nanosecond to microsecond pulses, which is typical in case of a Q switch laser. Okay. So if the recovery time is less than the gain, decay time, more log pulses we can get. If the decay time and the recovery time is almost equal, then we get unstable kind of Q switch pulses. But real Q switch pulses we get when the recovery time is greater than the gain medium's decay time, and in this case we get Q switch pulses nanosecond to microsecond. Okay, and here also a comparison. You can see that gain medium and saturation. So whatever the gain medium we use, we have to decide, or we have to choose the saturable absorbent according to that, comparable with the decay time. So Andy Yag, on this scale you have a decay or recovery time. Okay, so Andy Yag having a longer decay time, okay, dyes have less, and organic dye having a longer recovery time, and sesames have shorter recovery time. Okay, and keep remember, like in the previous slide, recovery time smaller than the decay time of the gain medium. Decay time of the gain medium, then this is the condition for to have a mod log pulses. So what do you see here? This is animation. What it shows, on left side you have mod log pulses, okay, and on the right side you have kind of Q switch pulses, okay, and the same thing is you can see here. On the left side, what you see, these mod log pulses, I mean, if you could see these pulses on the oscilloscope, if you know what is oscilloscope, probably it's exactly the same. It appears like this on the oscilloscope, the mod log the pulses. So mod log pulses, it means that the recovery time of the absorber is less than the decay time of the gain medium. And here on the right side, this is giant kind of pulse, Okay, longer duration, and but in this case, the absorber is slower than the gain decay time. Okay, so I hope this visualization, what I do actually, it may help you to understand, to take some image, understandable image in your brain, that how it works somehow. Okay, so move to the next slide. This is how to show graphically. Left side, actually, what you see here, this is for the saturable absorber, okay? And here on the right side, you have a gain medium, amplifier medium or gain medium, whatever you want to say. So what happened in the beginning, this is the intensity, okay? What happened in the beginning when the intensity is low, this is a transmission. Okay? When the intensity is low, the transmission is also low, almost zero. So when the intensity is increasing, and along with the increase of intensity, the transmission is also increasing. A stage will come when the transmission will be maximum. And when the transmission will be maximum, you compare with the gain medium's intensity pattern here. In the beginning, the intensity is low, the gain is high. Okay? I'm not saying about the losses. The gain is high. So with the passage of time, when the intensity increase, the gain become lower. Okay? So why it become lower? Gain saturation. Gain saturation. Okay, it needs to pump. Continuous pumping is necessary. Okay, so what left plot is showing, that is saturable absorber intensity versus transmission, and with the passage of time, intensity increases and the transmission increases. On the right side, what you see is the gain medium, and gain is decreases with the intensity. If the intensity is increasing, the gain will be decreasing because it's a gain saturation. And you need to keep pumping or this kind of things to keep it working or something like this. So this is how both the things in the cavity, it works. Okay. So when this transmission actually reaches to the peak, gain is peak at the time and the lasing action is started, and along with this one, the gains is started to reduce because of the gain cycle, because the next pulse will come and the same process will be repeated. Okay, so what exactly happens here, that at zero time, and the pumping is going on, but the intensity is very low, so it's opaque, nothing will go out, losses are very high, and initially gain is very high because it's unsaturated, and with the passage of time, this gain will be reduced because of gain saturation concept. Okay, and the power rises, spikes at very high intensity, the absorber will become transparent, and you get the peak at the output. Okay, and losses are much less because we are getting something at the output. Okay, and unwanted pulses or low intensity pulses or something like this, they are faded out. Okay, they are removed somehow, and It's called a gain competition in the sense, it's written here, gain competition, that because the strongest spikes wins, they go out, and the weak spikes may not be able to go out. So they cannot win the race. So if everything works fine, then what you get at the output, that intense pulse that carry almost all the energy. Shorter the time, more the energy. Okay, the peak power, something like this. This is also animation. I mean, it will also help you to understand. Like you can see on the left side, the transmission saturable absorber, and on the right side, you can see the gain versus intensity. Okay, so intensity is increasing, transmission is increasing. On the other hand, intensity is increasing and gain is reducing. Okay, reason I mentioned in the last slide. Okay, so rise of a transmission, at the beginning you have a very high gain, and the gain slowly decay down, so that the pulse, so that the situation will become that the intensity will become low, and it will be blocked or absorbed by the saturable absorber, and then this process is repeated again and again. Okay, so this graphical representation may help you to understand how it works. Okay, so important thing now. It generates the mode lock pulses. Okay, and it not only generates the pulses, it also helps us to get shorter pulses. What you see here, this is a saturable absorber here. Okay, this is input pulse, this is output pulse, and here we have amplifier or the gain medium, input pulse and the output pulse. So what is going on here, that this is your initial pulse before to pass through a saturable absorber. After it passes through a saturable absorber, low intensity is blocked. This leading edge of the pulse, it has a low intensity here. Okay, so this portion will be reduced, and this spectrum, or this is temporal actually, we are showing this portion will be squeezed, like here. You can clearly see. Okay, so pulse becomes shorter. Okay, so the characteristics of this saturable absorber, to absorb the low intensity portions, it helps you to get a shorter pulse. And if you go down here, and this is the amplifier, gain medium, you have initial pulse here. What amplifier does? Amplifier, it increase the peak and amplify the signal. Okay, and when it amplify the signal, this is the purpose of the amplifier. Amplifier, I mean, like in the gain medium, so in the cavity, you have a gain medium, and the light passes through this gain medium again and again. So it's amplifying as well. So it means that amplifier increasing the peak power and increasing the strength of the pulse. And after that, saturable absorber squeeze this pulse by absorbing the low intensity portion of the pulse. Okay, and this is how you can say, like, it works, and you get shorter pulse. Before to go further, Let me just a minute. I have to unshare and then share again. You people can see something or not? David, what you see now?
The presentation was not at full screen.
Just a minute. Okay, just a minute. Okay, so you people can see again, eh? Yes?
Yes, sir, we can see.
Okay, okay, thank you. So you people usually don't reply. I don't know why. I don't think it's very boring. I'm not saying it's very interesting, but it's not very boring. I think some things are very interesting here. So if you go to the next slide, just a minute. So what do you see here? David, what you see here now? Okay, so upper portion is showing the absorbing effect. Down portion is showing the bleaching effect. Okay, bleaching, it means it's release the pulses. Okay, squeeze and release. It automatically squeezed. And the upper portion is because, I mean, the pulse height I'm showing the same, which is not correct actually. Here, in this case, the pulse height has to be less. So the weaker pulse, it will absorb here. We don't see anything output. And the stronger pulse here, it will pass through. This portion is transparent for this pulse, and we have a squeezed and uh, energetic pulse at the output. Okay, so you can say that here it has to be less, not that much intense beam. It is like this pulse, and here it has to be like this pulse. Okay, so this animation, I mean, I think it may help you to understand how it works in the cavity if you have a saturable absorber in the cavity. This one also, on the right side, you can see the graphic pattern here, and the pulse is moving to and fro, back and forth in the medium, and you can see that when it reaches to the saturable absorber, then we get, this is showing the maximum transmission. So maximum transmission, then you have very nice energetic pulse at the output. So this graphic pattern, actually, it will help you to understand actually this is how the things are happening in the time domain. Okay. Okay. Second kind of passive mode locking, we call it Kerr Lenz. Kerr was a scientist actually, and Morshio, he knows the Kerr effect actually, he studied probably. This mode locking concept is much more practical, and for this kind of, you don't need any external device actually in the cavity. But it's hard to understand this concept. In short, it's called KLM, Kerr Lenz mode locking. Okay, so number of points and number of, you can see the number of points are written here to understand what exactly it is. So this is a mode locking concept. And in this kind of mode locking, medium, the gain medium is playing the important role. Gain medium itself. One slit may also need, it depends on the, but slit and the Kerr medium. Kerr medium is like gain medium, okay? One thing, if you see this equation here, intensity dependent refractive index, okay? N is equal to N naught plus N2, right? So any effective refractive index, N naught is a linear refractive index, N2 is a non-linear refractive index. Second order, maybe. L intensity of the incident beam. So there are materials, almost all actually depends. The refractive index changing with the intensity, but it has to be very intense. Of intense beam of light or something like this. So that is why it's mentioned here, strong light changes the refractive index. And it forms the concept of what? Self-focusing lens. You will see in the next slide what is this self-focusing. So what exactly it happens? Like very intense beam passed through the gain medium and it focused after passing through. It's focused itself. Because the light is passing through is very intense, very high intensity, and the gain medium through which this light is passing through change its refractive index because the light is very intense. It has to be very intense. If it is not very intense, nothing will happen. Because you can see in this equation. So the second order refractive index, actually it depends on the intensity. Okay, so here the pulse selection, the intense pulse, like in case of saturated absorber as well, which focus itself actually and pass through the slit. We use the slit in the arrangement, and the weak pulses actually they were stopped by the sides of the slit. You can see the next slide. I'm coming the arrangement, what kind of arrangement it could be, and cavity optimization is the same thing. Like it has to be well aligned, and short pulse experience higher gain and dominant because of this effect of intensity dependent refractive index. So how this kind of the mode locking is started, this initiation of this effect, you can say. A small disturbance. Okay, it's, let's say on the optical table, we introduce a small disturbance, jerk, shake a bit, and mode locking will be started. And this is kind of a strange thing to understand, but it exactly happened. When you give a little jerk, I mean, like shake a bit, the optical table or the optical components there, the mirror mounts or something like this, then this Kerr lens mode locking is started. It kind of uh, intensity fluctuation. We needed in the beginning kind of intensity fluctuations. So that intensity fluctuation causes is to have a Kerr lens mode locking. Okay, so what you see here, this is the formula, same formula. And this is the kind of, not kind of, it is in the category of passive mode locking and Kerr lensing, as I explained now, you can see here. If the intensity is low intensity beam, okay, you can see here, it passed through. Okay, this one is Kerr medium. Okay, so Kerr medium is there, but through this medium, the intensity of the light was very low or lower somehow. So we don't see any kind of effect of self-focusing. In the previous slides mentioned self-focusing. So second order refractive index, okay, not the first order refractive index. Now, if the intensity is higher intensity, okay, and what happens after passing through the Kerr medium? It focuses itself here. Okay. The condition is the intensity, high intensity. Okay. So this is self-focusing. Very intense light passes through the Kerr medium and self-focusing. And this self-focusing is the key to mode locking, of Kerr lens mode locking. Okay. So now, step by step to explain this thing. It's also called self mode locking. Kerr lens mode locking is also called self mode locking. Actually, to generate or to create the mode locking, sometimes people use the mechanical things as well. Initial fluctuation in the intensity is needed. But initial intensity fluctuation you can also generate just by touching the table, shaking it a bit or something like this. So what happened in the beginning here? This is your gain medium, amplify medium you can say, or whatever you can say, and this is medium. When through this medium, intense light passes through, a kind of a virtual lens, which you call Kerr lens actually, is created. This is you people to understand. It's not exactly lens is created there. So the light when passed through, intense light, it squeezes here and it's focus, sorry. Focus here, self-focusing. Anyway, first thing is that what is mentioned here, a kind of virtual lens is created, okay? And intense light, the outer portion of the light may not be as intense, okay? Like this is the Gaussian distribution, okay, the pulse. The inner part of the pulse is more intense, so it feels more self-focusing effect as compared to the outer part of the weak field. Okay, so that is why you may need to use a slit here to stop the unwanted part of the light, but let the other part to pass through. This is the I mean, this is the process which is going on inside the medium or amplify medium, gain medium. But why this thing happen? Not why actually. If you have same medium, if you have a very low intensity laser beam pass through, nothing will happen. This effect will not appear. But if you have very intense beam, then this effect will appear following the equation, which is n is equal to n naught n 2I. This equation tells you everything. Intensity dependent refractive index. Next slide. The light is passing through, okay, and outer portion I mentioned that weak. Now, you know that in case of cavity, you have a pump as well there, and the laser photons are also moving to and fro, back and forth, and pump is also there. So this pump is actually help to optimize this mode locking, lens mode locking or self mode locking phenomenon. Okay, you can read here what it says. A pulse train is generated by introducing different gain for continued pulse waves, achieved by adjusting the pump beam size. Okay, what is the pump beam size? Pump beam size is supposed to be the same as lens is created here, virtual lens. If the pump beam size is bigger than this one, so you may not have optimized pulses, more lock pulses. So pump also plays an important role. But the main laser beam, which passes through again and again through the medium, amplified medium or the gain medium, that is the main thing who make possible that lens mode locking. Okay, so now here they show that why do we need to put the slit? Simply to block the weaker region, we only need the central portion which is self-focused. Okay, so the outer portion is blocked. So the light will only pass through, which is the intense one, and which is the mode locked one, through the aperture. This is called hard aperture. And the previous one, it is called, there is no hard things around. This soft aperture created by adjusting the pump beam dimensions or diameter or dimension, you can say 1 millimeter, 2 millimeter, it depends on you have to optimize manually sometime. Okay, so this is how it can be animated. It may not be 100% what exactly it's supposed to be, but it will help you to understand that weak light is blocked. Okay, and if the weak light blocks, the intense one pass through. Weak light, which is on the sides, this portion is weak light. Okay, so there are two, you can see the two pulses, I mean, two color pulses. One is red and other one is faded red, very dim kind of red. And on the right side, you can see the graphic pattern. On the left side, you can see that the cavity. Okay. This one, this is a low intensity pulse, which is blocked by the aperture. And the intense one, it passed through, which is the mode locked pulse. And same thing here. The intense one is dominant, and the weaker pulse, it's faded out, extinguished. Okay. So this probably it may help you to understand. The care medium is there, which is titanium sapphire. Titanium sapphire is the most famous ultrafast laser medium, actually, again medium. And when it passed through, the pulses amplify there, but the low intensity pulses are passing through there, but it blocked with the aperture. So the intense mode lock pulse will be going out of the output coupler, or we get the output. Okay. This is, if you remember, can we distinguish laser output by their time scales? So before I will press a next key, what this figure actually is showing here, and what this one, and what this one, and what this one. Who will tell me? Amna Said.
Sir, in the second one there are pulses,
Okay.
and the first one is a discontinuous line. Sir, I don't know.
No, it's okay. I mean, you can try. And the third one? Third one, this
Sir,
one.
in the third we have
Yeah, this one.
pulses.
And here?
Here are also pulses, but
Mhm. Did you go through my previous lectures, Amna Said?
yes, sir.
It's okay, no problem. Zanfar,
Yes, sir.
tell me, what's showing the first one?
Sir, it's the
It's a
constant
power
power.
versus time. So what it shows, this line, the red line.
Sir, it's the actually the energy. This line, red line showing.
No, I'm not saying it's
Uh,
energy or
cost
what. I mean, what it shows, what kind of laser it is.
continuous.
Continuous is what I'm saying. And the second one,
It's the pulse laser.
and the third one,
The third one is the mode lock laser.
and fourth one.
Fourth one is the sharp kind laser.
In the third one, do you see any kind of modes here?
Uh, s- these
You
are
see mode.
the
So if there is no mode, then it means it's not a mode locked. It's not a mode locked actually. It's a pulse, but it's not mode locked. On the other hand, you see the modes here. These are modes.
yes.
Okay. So modes in a pulse. Okay. So, okay, somehow you did something, but maybe. Okay. Nargis, did you understand this thing?
Yes, sir. Sir, for me, like it's if we distinguish the laser on the basis of their time scales, so there are continuous wave lasers and discrete or like pulse lasers. So I
Okay.
think in the first two there is continuous wave lasers because we can't see any sharp peaks there, and in third and fourth, there it is discrete or can say the pulse laser. That's what I'm getting.
Yeah, I mean, it's good you tried. But this one actually, you can see these are it cannot be continuous, second one. Okay.
Okay.
So now see, First one CW. Second one CW mode locked. Okay. Third one is Q switched laser. So, and the last one is Q switched mode locked. Okay. So CW mode lock means there are no pulses, but it's mode locked. Here there are pulses generated with the Q switching, and here with the Q switch and mode locking. Inside the Q switch, because Q switch is nanosecond or something like this. So many modes can be in the one pulse here. So you can say this is a mode locked, the last one. And this one is obviously Q switch pulse. Okay, Zanfar? And this one is, because it's not a straight line, it has something. It is mode locked because you can see these modes. Okay, so modes are logged there, but modes are not logged in a pulse. Okay, so this is, okay, this was just for to recall your memories, I mean. Now, you have to know a little bit about the titanium sapphire. Why titanium sapphire is important and why it is more widely used actually in this kind of ultrafast lasers. You know already, I mean, some things I have mentioned already, that the titanium sapphire actually is a titanium doped sapphire. Formula you can see here. And it's a 4-level laser system. 4-level laser, so it's easier to pump, obviously. And you have a metastable here, and then decays and you get some lasing. It's tunable as well. Tunable in the sense that you can also have ultra-fast laser or femtosecond laser in the range of 1000 nanometer, and you can also have around 700 nanometers. Okay, so tunable, it means you can have the pulses in this range as well. It's not possible to have at the same time, but you can tune. Okay. And absorption band is very important. If you remember the beginning lectures problem, the absorption band actually is important in the sense the pump we use, it has to be according to that band. So that light is supposed to be absorbed and then stimulated emission, population inversion, etc., etc. But the first thing is that the pump has to be in the range of the absorption band. Okay, so absorption band in case of a TISF is 400 to 630 nanometers. Okay, and peak around like 490 or 500. Much better to have pump source who's around this value. So titanium doping is 0.1%. Okay, and it has a short upper laser level lifetime, which is only 3.8 microsecond. And pumping source, actually, I mentioned before that ND YAG, second harmonic of ND YAG. Okay, because we don't need 1054 or something like this. Second harmonic of, it means the second, so half of this one. So it's around 528 or something like this. Okay. And argon ion can also be used, but it's not very common. Mostly ND YAG is used or ND WALF. First, these are Q-switched lasers, which are used to pump these TISFs. Okay. And it's high thermal conductivity, good mechanical rigidity, good chemical. The advantage of this one, it does get heat up, but it's not like after heating to break down its crystal structure or something like that. We need a cooling system, but still it's very good thermal conductor, and it has a good mechanical rigidity. It's not easily broken. And less power is needed to create and sustain the population inversion. It was 4-level system, okay? And also depend on the decay time. And it emits 650 to 1100, as I mentioned that. And it has applications, but tunability is one of the things which is very good. And this is one of the reasons we have ultra short pulses in a different wavelength ranges, actually, starting from 700 to 1000 nanometers. And pump, as I mentioned, that it has to be in this range, matching to the absorption band. Okay, argonine wavelength is 514 and ND-YAG is 532, second harmonic generation. Second harmonic generation, you people may not know, some of you people. This is a non-linear kind of crystal. There are different kind of second harmonic crystals. So what we use, I'm not going in detail of that one. Second harmonic crystals are used if we want to double the frequency or half the wavelength. Okay, so if some laser is emitting 700 nanometer, if we use this crystal, when it passes through this laser, when pass through this crystal, we get 350 nanometers. Okay, so this is also called frequency doubling crystals. So here we are not doubling the frequency, we are using the wavelength, so half the wavelength. Okay, so these crystals are also available and frequently we use in a laser system if we need some wavelength which are not existing. So we can use these kind of crystals so to have that wavelength range. Okay, so titanium sapphire is the key to use ultrafast, to build an ultrafast laser. Okay. Now you can see that absorption and fluorescence. Okay, so or absorption or emission spectra. So here, if you see, this is the absorption range where you use the pump. You have to choose the pump in this region, and this is the output absorption, not absorption, sorry, output of the emission. So in this range, you can get the output if we use the titanium sapphire. Titanium sapphire can also be used in the CW form. It can be CW form, it can be Morlock form. So it's versatile kind of things, and you don't need a very big crystal for this kind of things. Small crystals, actually. Maybe you will see in the next coming lecture the size of the crystal or something. I will show you the slide somehow. So last 2-3 slides here. What is so special about the ultrafast or femtosecond laser? Obvious, you have the shorter pulses, okay, and important thing is that why do we need to have shorter pulses? Shorter pulses, femtosecond range pulses, it's very short time. So we can excite the species in such a short time. We can understand, we can see the molecular reactions somehow, that femtochemistry, we call it femtochemistry. One of the applications, there are many applications actually. And so the dynamics of the excited state can be monitored with the higher temporal resolutions. Higher temporal resolutions. So that is 12 to 15 femtosecond. Okay, so if we have shorter pulse, we can understand the dynamics of some excited states in a molecular reaction or whatever it is, because high temporal resolution, very short time, femtosecond. And even the visualization of ultra-fast dynamical process is also possible, that excited states, absorption, etc., etc. This is purely related to the femtochemistry, this kind of things. And other things is peak power. If the pulse is shorter, then you can have very high peak. But here I mentioned gigawatt. Gigawatt is nothing actually. Now you have petawatt. Okay. So like here, if you have 1 millijoule pulse and 100 femtosecond duration, so it means the peak power will be around 10 gigawatt. 10 gigawatt peak power is a huge peak power. Okay. But now you can even have petawatt. Okay. And you have to figure out megawatt is equal to how many watt, gigawatt is equal to how many watt, 10 to raise to power what, and petawatt. Okay, you have to figure it out. And even 10 petawatts is petawatt is already, generated. 10 petawatts also generated. They are moving towards more higher peak powers. So more higher peak powers is essential. You need it for the fusion reaction. One of the example, there are so many reactions to accelerate the electrons and etc. So you need these kind of things to study multi-photon absorption, optical harmonization, material relations, and spectroscopy, etc. So many applications. So, because the question was here, what's so special about ultra-fast femtosecond laser? If you remember, this thing also for your memory, longer the pulse here, and you will have narrow spectrum. Okay. But if the pulse is short, you have a very broad spectrum. Okay. So, because we need many modes to be logged so that we can have shorter pulse. And in case of a longer temporary longer pulse, the spectrum, we don't need a very broad spectrum. It will be very like a line may have. And you can have very long pulse millisecond, like not picosecond, milliseconds and some microseconds or nano being also considered or something like this. So broader the spectrum in the frequency domain, broader the spectrum, shorter the pulse, and narrow the spectrum in the frequency domain, and broader will be the temporal, the longer will be the pulse. Okay, so this is just to recall your memories. Now, simple question, that light bulbs, lasers, and ultra-fast pulses. We know that the light bulb is incoherent, okay? But in case of ultra-fast pulses, we need a broad spectrum. In case of bulb, we have a broad spectrum. White light spectrum is very broad as well. If you use a spectrometer and take the spectrum, it will be very broad. Okay, from blue to something red, something like this. And same in case of a ultra short pulses, we need a broad spectrum. Okay, maybe it's coming from 600 to 1000 nanometer or something like this. Here is also broad spectrum. And for ultra fast laser, we need a broad spectrum. Then why not here? Why can't we have this one? We say that this is also ultra short pulse. It's not first thing, it's not a pulse. So what exactly we need to generate or to make an ultra short pulse? We need what? Rutherford, what we need? What exactly is required to make an ultra short pulse? Zanfar. Nargis.
I'm here, but I could not get it. Means there are so many things to make it like a pulse. What have we
No,
studied?
no. There is one thing actually. One thing is important. Okay, let me ask other. Ihtisham,
I think, as you said, the bulb light is incoherent. Coherence is the most needed thing here.
no. This is what I'm saying to generate the pulse. I'm not saying to generate the laser. David, did you get any idea? What exactly is required to make an ultra short pulse? David,
Sir, mod
Sir,
locking.
just a minute, Nargis, just a minute. Yes, David? 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 Okay. Nargis, say it again.
I was thinking of the mod.
Yes,
I
you
was
are right.
thinking the
you are,
spectrum means there are multiple modes. If we sometimes
yes, you are right.
able
So,
to-
yes. So you are right. The main thing is that that is mode locking. Okay. So the answer is mode locking. So mode lock laser. So ultra short pulses can only be generated if you have mode lock laser. If there is no mode locking, then you don't have ultra short pulses. Locking of the mode is necessary, not the eliminating of the modes. Okay. This one you already know. I have shown this kind of slide before just to recall your memories that here, what you see here, that is random pulses, okay, out of phase. And at the output, you don't get anything. This is just a noise. And if the pulses are logged here, these modes are logged, not the pulses. Modes are logged here. These are modes, different wavelengths are logged. Then at the output, you get this ultra short pulse. When this thing is not logged, there are so many modes. In case of a bulb light, or in any other case, any other laser, but you don't get the pulse. You just get something random noise, or maybe simple spectrum. But something is logged here, then you get this pulse, ultra short pulse. Okay? Remember this thing. Okay, so probably last slide. What you see here, Zanfar, is your turn now.
yes, sir.
What do you see here?
Sir, this is the mode lock,
Yes, more logs.
and in first we have the 50 mode locks,
Mhm.
and we have the high intensity.
Mhm.
Yes, and we
Mhm.
and secondly we have the uh, phase relation. Some phase relation means we have the some uh, some pulses we are getting out from this.
Okay, give me 1 minute. I have Azan is going on, so. Okay. Okay, Zanfar, now tell me.
Yes, sir. Sir, we have
Yes, you were right before. Say.
sir, there are many waves inside the cavity. When the waves get in phase, we get the mode lock
Yes.
laser.
Yes. And what this figure is showing now?
There are the two wave mode lock, and these have the 50 mode locks
Mhm.
inside the bandwidth of the gain medium,
Mhm.
and other than we get zero intensity.
Mhm. Mhm. Okay, so the thing is that, I mean, you people can clearly see that it depends, I mean, how many modes you can lock. So more modes, if you can lock, then you will get proper intense pulses. Okay, so here in this case, this one actually showing the temporal profile here, and this one is how many modes are there. So frequency modes, okay, this one. This is a time domain. So if you have logged 50 modes, you get this pulse, okay? And if you logged 5 modes, you get this, okay? So it means if you really want to have ultra fast pulses, you need to lock as many modes as you can, okay? So you have broader spectrum. So if the 5 modes are logged, it means the spectrum wasn't that much broad. So you get something, but it's not that intense pulse, and it can never be a femtosecond pulse. Okay. So this is what is showing actually. So there are a number of modes here, and these modes are randomly moving, and whenever they lock, then a giant pulse is not giant actually, a short pulse is generated. Here, this side, and here on this side. Whenever they are locked, then you get the short pulse. Whenever they log, you get a short pulse. If it is not locked, you cannot get anything. Otherwise, you have CW or something like this. Some small pulses. I mean, if there is a little locking is going on. So this is just to interpret. I mean, how it can be shown that the logged modes. Okay, so this was the last slide, and I hope you understood something. So if you have any question, you can ask. Any of you? Few people are here today. I don't know how many. Yes.
I have a question.
Sure.
Sir, I understand about the curve lens that it is a virtual lens and it is somewhere generated in the gain medium, which is in the cavity for the
Yes.
generation of laser. But
Yes.
what was the exact reason for its? I could not get it that much.
Exact reason of what?
For the generation of the curve, is it to be called as region? Can we call it like if it is in a gain medium and it is a
Yeah.
portion of the gain medium is behaving like the curve lens, so it
Yes.
can be called as a region.
What do you mean by region?
Region means a specific area where the part of the gain medium is behaving in this way.
The
Or am I
gain.
getting the thing
No,
is
actually,
wrong?
when the intensity, I mean, intensity is very high, that gain medium automatically acts as a lens, virtual lens.
Okay, the whole of
So
the gain mediums, not the
yes,
part.
whole of the gain medium.
I was thinking a specific part is behaving in a.
No. Whole of the gain medium actually,
Okay.
because it entirely depends upon the intensity of the beam.
And the refractive index.
Yeah.
Okay, that's good.
Okay. So David, do you have any question? David, are you there? I think you didn't have breakfast today yet. Is it? Okay. That is why you are feeling hungry, probably. Okay, so Russia, you have any question?
No, for the moment. Maybe later in the chat.
Okay.
WhatsApp we can ask.
Okay. Ihtisham.
So I have a question that can we say that passive mode, in the case of the passive mode blocking, we are only doing amplitude modulation, and while in the case of the electro-optic modulation, we were doing the frequency modulation also.
No, you cannot say like this. It's
So
not
in
only
this case,
amplitude modulation.
actually, I didn't understand the frequency modulation part of this passive mode blocking.
You can go through first, and then we can discuss. Actually, it's first you have to understand some basics of it. Okay, and then we can.
Thank you.
Anytime welcome to discuss. Okay, so Ghazanfar, definitely you don't have any question.
No, sir.
You are already expert of ultrafast, isn't it?
No, sir, I'm not expert, but it's a basic thing yet.
But I want you to be expert. I want you to be one of the expert. Or I want to make you expert, probably.
Inshallah, sir, inshallah.
Amna Said, question?
Sir, I didn't get the point that Nd:YAG lasers cannot be femtosecond lasers.
Because of the decay time. Their decay time is very long. It's impossible to have more short pulses. Okay, you can have a giant pulses, Q-switch pulses from the Nd:YAG, but not the short pulses. Decay time, you can go back and you can see the decay time is longer. It's here, 230 microsecond and 3.2 microsecond, huge difference. Okay, so this is the reason.
Okay, sir.
Okay,
and,
so
sir,
yes.
Sir, is repetition rate frequency?
You can say it's repetition rate. I mean, it's frequency. What is the frequency of the pulses? After how many, seconds or minutes the pulse comes? So it's the frequency. F is equal to 1 over T.
Okay, sir. Thank you.
You're welcome. Okay, so probably in the next class, we will have something more and more towards the ultra short pulses. How to generate the ultra short pulses. And like oscillator, certain kind of technique or something like this. And so probably within 15, probably four more maybe lecture or something like this. And one more thing actually I want to mention here, that I am going to start a kind of consultancy if the students wants to apply for MS or PhD here where I'm living now. And that would, like here it's definitely it's a European country and they are in the European Union. And if students are interested to apply here in the masters and in the PhD, so probably they can talk with me about this kind of things, because there are some chances of the scholarship also. There are chances without fee as well. There are some chances definitely with the fee. Even with the fee, actually, it's not that much high as compared to other part of the Europe yet. Even if I compare with Pakistan, I mean the universities, which are really considered to be good universities like LUMS or something like this kind of nest or something. So how much do they take for this masters or something like this? I mean, probably here it's comparable, or in some cases, maybe at least from lungs, it's less problem. I'm not sure, maybe. So you people can spread my words. If I will post on the social media as well. If some of the students, they are interested to apply in the masters or and the PhD level in the physics or related subjects or something like this. So they may, I mean, contact me because the application process is not that much simple here. It needs quite a bit of understanding. So this is what I wanted to say at the end. So we'll see in the coming week, next week, probably same time, and with some new slides and with some new concepts. Most probably new for all of you, because this is not a very usual kind of course in most of the universities. And thank you very much for attending and sparing your time to attend this class. And soon, probably, I may share with you the kind of assignment or homework. And so probably you people can submit. So thank you very much. And have a great week ahead. See you in the next week. Okay, goodbye.
Hafiz, sir.
Allah Hafiz.
Thank you.